Okay, maybe I'll get started. I hope you can hear me clearly. Just a couple of announcements to begin with. One of them, of course, is the reminder of the exam. Here we are, Tuesday in our regular lecture room. It's 10:30 to 12:30. It's the same format as the two tests. It has the true false. There'll be 15 true false questions. It has the numerical answers. There's 7 numerical answer questions, and then there's 3 problems, fully worked out problems with partial credit. So that's a 50% larger exam than either test 1 or test 2, but the same format as test 1 and test 2. The other thing I think I wanted to say is that in this review, I'm going to go through a number of review slides that include the material, try and cover the material from the semester, and some examples of problems from the semester. Also, on our Canvas page is recordings of my solutions to a practice test. So you can also take a look there at the Zoom recording of my solutions to a final practice test. So maybe that's useful also. Any questions on that before I go on? I'm going to try and watch the chat. And my record of that is partial success. So you can always shout out if you've got questions also. Okay. So I'm going to work through the material from the semester. That's material on electricity, magnetism, and then induction, the joining together of electricity and magnetism, and then light, which was a product of the joining together of electricity and magnetism. And then finally, the work we did on special relativity, space and time, and wave-particle duality, quantum physics, that actually came out of our understanding of electricity and magnetism. Okay, so I'm going to begin here with the electric force. And when we talked about the electric force, we talked about it being a force or an interaction between electrical charges. So that was the dimension of nature that caused the electrical force. And we introduced 2 important concepts to help us understand the electrical force between electrical charges. One of them was fields, electrical fields that transmit the charges. One of them was electrical potentials. We can also think of as conveying the forces. And we define these 2 concepts downstairs here in terms of things that we could measure, which are the forces between a pair of charges and the potential energy of a pair of charges. And so this was an important equation for us because it introduced the electrical field in terms of the electrical force. It introduced how the electrical field carries the electrical force. And this was an important equation over here on the right. This defined for us the electrical potential and how it's related to the potential energy of an arrangement of charges. So those were very fundamental concepts as we started working on electricity. So to work with the electrical field and work with the electrical potential from a practical perspective, we introduced equations for the electrical field that surrounds a single point charge and the electrical potential of a single point charge. And so that's these two equations on this slide. This one over, oh, I'm going to do that all the time now. This one over here on the left-hand side, this is the electrical field of a single point charge. And this one over here on the right-hand side is the electrical potential of a single point charge. And so let me just make some remarks about the field and the potential of a point charge. So the field is in proportion to the amount of charge. So that's an important point. The more charge, the more field surrounding it. Less charge, less field surrounding it. The field falls off as, with distance from the charge, it falls off as the square of the distance from the charge. So that's an important point. If you double the distance from the charge, the field will be 1/4. If you triple the distance from the charge, the field will be 1/9. The field is a vector. So that field has a size. This is the size of the field. Also has a direction. And that direction is radially outwards if you've got a positive point charge, and it's radially inwards towards the charge if you've got a negative charge. So that's the electrical field of a single point charge. What about the electrical potential? So the electrical potential also is in proportion to the charge. So the more charge, the larger the surrounding electrical potential. The less charge, the smaller the surrounding electrical potential. It's also proportional to the distance from the charge. It falls off with the distance from the charge, but it falls off as 1 over the distance, not 1 over the square of the distance. So if you double the distance from the charge, the potential will reduce by a factor of 2. If you triple the distance from the charge, the potential is reduced by a factor of 3. And then finally, an important point about potential is it's a scalar quantity. So it has a size that can be positive or negative, depending on whether you've got positive and negative charges, but it doesn't have a direction like the electrical field has a direction. So that's an important difference. For positive charges, the surrounding electrical potential is positive. For negative charges, the surrounding potential is negative. And so that's kind of a summary of the electrical potential of a single point charge. For those equations for the electrical potential and the electrical field to be very useful, we actually supplement those two equations with what's called the superposition principle. The idea of the superposition principle that comes up for electrical fields, it comes up for magnetic fields in many circumstances too, is that the electrical field of a collection, assembly of charges is simply the vector sum of the electrical fields of the individual charges. And the electrical potential of a collection of charges is simply the sum of the individual potentials of the charges. And that concept is depicted here for the electrical field and here for the electrical potential. So the total field of an arrangement of charges is just the sum of their vector fields. The total potential of arrangement of charges is just the sum of their scalar potentials. And there's the big difference, right? Electrical field is a vector. Electrical potential is a scalar. It means it's harder to add up the electrical fields to get the total electrical field because you're adding vectors. It's generally easier to add up the electrical potentials to get the total electrical potential because you're just adding up numbers. Here's how you might picture the superposition principle for a couple of charges. creating a couple of fields. So E1 is the field of charge 1, E2 is the field of charge 2. You add those vectors together to get the resulting electrical field of the two charges. And here's how you might picture the same situation for charges 1 and 2 for the electrical potentials. Here you just have to add the numerical values of the electrical potential of charge 1 to the electrical potential of charge 2 to get the total electrical potential. So here's a little illustration of electrical fields, electrical potentials of point charges. In this case, just 2-point charges, an equal and opposite positive charge. It's an illustration of the superposition of the fields of the two charges and the potentials of the two charges. And it's also an illustration of how we sketch or draw electrical fields and electrical potentials. We often sketch electrical fields with what we call electrical field lines. And we sketched electrical potentials with contours of electrical potential. So for the electrical field lines, that's the lines in orange here of this charge distribution. The key points are that if the lines are closely packed, say in the neighborhood of this positive charge or in the neighborhood of this negative charge, then that's a region of strong field. If the lines are loosely packed, say upstairs in the top left here or downstairs in the bottom right here, then the loosely packed field lines corresponds to a region of weak electrical field. And then the direction of the lines of field, that indicates the direction of the electrical field. So if you look along this midplane here, it's an interesting thing. The field lines are just sweeping left to right along the midplane, and the field is left to right along the midplane. If you look in the neighborhood, neighborhood of the positive charge, you see the field lines are coming radially outwards from the positive charge, and that's because the field is radially outwards from a positive charge. If you look around the negative charge, the field lines are going radially inwards towards the negative charge. That's because the field itself points radially inwards towards in the neighborhood of this negative charge. And so that's how electrical field lines are very handy for sketching electrical fields and for sort of visually conveying an electrical field. The electrical potential, as said, we describe with contours of electrical potential. And so you can see these contours in this sketch here. Let me just, here's one. Oh, no. I'm going to do that all the time today, I'm sure. Here's a contour of electrical potential around the positive charge. Here's a contour of electrical potential around the negative charge. And everywhere on a particular contour of electrical potential, the electrical potential has the same value. So for example, over here on the right-hand side, around the positive charge, this might be +1 volt. And over here on the left-hand side, around the negative charge, maybe this is minus 0.5 volts. Everywhere on that contour on the right, everywhere on that contour on the left-hand side. And so that's how contours convey the landscape of the electrical potentials. Okay, question in the chat. Is the potential 0 at the center line or the field? Okay, that's a great question. So at this center line, the electrical potential is 0 everywhere along that center line. That's because the electrical potentials of the positive charge and the negative charge are equal in size, opposite in sign. And so they cancel out and produce an electrical potential at 0 everywhere along the midplane. The electrical field, on the other hand, is not 0. And you can see that because there are field lines here along this region here. At any point here along the midplane, the field lines don't, the field doesn't cancel out for the two charges. So the result of superimposing the two fields along this midplane, because they're vectors, they're not scalars, is that they don't cancel out and they produce this field that simply sweeps from the left to the right. So I hope that answers that. That was a very good point. Okay, so here's a little example problem in which we've got three charges. And the three charges are arranged at these locations in the XY, in this horizontal plane. One's located at the origin, one's on the x-axis, and one's on the y-axis. And we're told the locations of the charges, we're told the values, numerical values of the charges. And we're asked to figure out the size and the direction of the electric force on the charge that's located at the origin. So what's the size and the direction of the electrical force on this charge located here at the origin due to the two other charges that are in its neighborhood? So that's our task. This is going to involve, the electrical fields of point charges. Is going to involve the superposition of electrical fields of point charges. So I would start, if I was going to solve this problem, I am going to solve this problem, I would start with a sketch, that's what I've drawn here, of the arrangement of charges. I would add to the sketch, the things I know, which are the quantities of charge at these locations, the positions of the charge. And I would also add on the sketch, you can see it here, the forces, individual forces that are acting on the point charge at the origin, and the net force, the resulting force, the total force on that point charge at the origin. And so, for example, F subscript 2(1), that's the force of the charge Q2 on the charge at the origin, Q1. And they're like-signed forces, and so that's a repulsive force. Then there's F(3)(1). That's the force on the charge at the origin to the charge Q3 below. And they're opposite sign charges, and so that's a attractive force. And so this guy here and this guy here are the two individual forces that are acting due to the two other charges. They're going to superimpose. One force will add to the other force. We could picture it like this, or we could picture it like this, to make this in magenta here, or in purple here, this resulting force. And our goal is to find the magnitude of this resulting force and find the precise direction of the resulting force, i.e. to turn this picture into a numerical value for the size of the force and the direction of the force. So that's our task now. Okay, so here we go. This is a problem of adding the two force vectors. And when you want to add two force vectors, in general, we break the forces down, individual forces down into their components in the XY directions, horizontal, vertical directions. We are then able to add up all the contributions in, say, the X direction, all the contributions in, say, the Y direction, to get the resulting force in an XY component language. And then finally, at the end, if we want the magnitude and the direction, we can convert the resulting force from the XY component language to the magnitude and direction language. And so I'm doing all those three steps, major steps, on this one overhead here. So let's just talk through these a little bit. So first step, we want to know the XY components of those two individual forces, the one due to charge number 2 on charge number 1, the one due to charge number 3 on charge number 1. that's what I'm doing in these two lines. So the top line here, this is all about the force of charge 2 on charge 1. The second line is all about the force of charge 3 on charge number 1. Now, there's a couple of important points here. Charges 1 and 2 were on the horizontal, the x-axis. And so the force in this case was horizontal. There was no y component. So that was easy. Likewise, for the interaction between charges 3 and 1, charge 3 was immediately below charge 1. And so the force is vertical in that case. There's no component horizontally. And so noticing that, observing that, seeing that, we quickly know that in each case, one component is 0. And actually, the force between charge 2 and charge 1, well, that's all, it's the entire strength is in the horizontal direction. So I can use Coulomb's law here for the force in the horizontal direction. Magnitude of the product of the charges divided by the square of the distance between them times the Coulomb constant. That will give me the size of that force. And I noted on the diagram, I didn't reproduce the diagram here, that that force, because it's a repulsive force between the two charges, is towards the left, the negative direction for the force on the charge at the origin. And so that's how I got this value here. So these are the two components for the first force in the pair of forces, that due to charge number 2. And then here's the same thing for the second force in this pair of forces. Again, this force is entirely vertically directed. It's all downwards. The magnitude is given by Coulomb's law. The product of the charges divided by the square of the distance between the charges multiplied by the Coulomb constant, which I left out here. There should be a K in here. And that will give us the strength of the force. And then again, I note from the diagram that this force, because that was actually an attractive interaction with a charge that was below the charge at the origin, that's also in the negative direction. And so that's how I got the minus sign here. And so that's my conclusions of kind of step 1. Then I'm going to move on and I'm going to add up the two x components from step 1, add up the two y components from step 1 to calculate the resulting x component, total net x component of the force on charge 1, and the resulting y component of the force on charge 1. And so this is my my second step here, where I'm really finding the resultant force. And in this x and y component language, it's really rather straightforward, really rather easy to find the net force, because you're just adding the numbers that correspond to the x components of the individual forces, or adding the numbers corresponding to the components, the y components of the individual forces. And if you do that, it's especially simple here, because in each case, one force is only acting horizontally, and one force is only acting vertically. These are the components of the x and y components of the resulting force. Okay, well, now we're almost there. Now, if we want the magnitude and direction of the force, we can just use a little bit of Pythagoras theorem and a little bit of geometry or trigonometry to get the magnitude and direction of the force. So if I want finally the magnitude of the resulting force, here I'm calculating it. I'm using Pythagoras' theorem, basically, that the x and y components make up the adjacent and opposite sides of a right-angled triangle whose hypotenuse is the net force, the resulting force. So all I got to do is square up the magnitudes of the x and y components, add them together, take the square root, Pythagoras' theorem, and I'm going to get the magnitude of the resulting force. And here it is, 14 times 10 to the minus 6 newtons. If I want the direction, there I can use a little bit of trigonometry. If I take the inverse tangent, arctangent of the ratio of the y to the x components of the resulting force, That will give me an angle. Actually, your calculator will give you one angle, but there's always two angles. There's an angle that is given by your calculator. Mine gave me 77 degrees. Then there's another angle that's the exact opposite direction. So you've got to add 180 degrees on here. It's 257 degrees. And these are the two possible solutions of the direction of that force away from the positive x-axis. And so then you would have to go back and consult your drawing, your sketch. I can do that. Here it was. Now it's all messed up, but that's okay. Look, this resulting force is this angle. Now, my work with the pen is not great. It's this angle away from the positive x-axis, and that's the 257 degrees. So let's jump back to the next slide. It's this solution here, the 257 degrees. Any questions on all that? I'm going through it pretty quickly because I'm panicked about the amount of material for the class. And because of that, I was drinking a lot of coffee. But anyway, this is how to solve that type of problem. One other way that we analyzed electrical problems, electrical interaction problems, was with a concept called electrical flux. And so I just wanted to remind you of electrical flux. If you want to visualize electrical flux, think about the lines of field. Think about a surface in that field, and the electrical flux is in proportion to the number of lines of field that are crossing that surface. That's how we visualize, picture electrical flux. You want an equation for the electrical flux? Upstairs here in the title, this is an equation for the electrical flux. If you've got a field passing through a surface, take the strength of the field, multiply it by the area of the surface, and multiply that by the angle between the electrical field vector at the surface and the angle of the vector A that describes the surface. And that would give you the flux through that surface. The interesting thing about the concept of flux is that we can think of electric charges as kind of either sources of flux, positive charges are, or like drains or sinks of flux, where the electrical flux goes. Negative charge are sinks or drains of flux. And that actually leads to Gauss's flux law, which I'm describing here. And Gauss's flux law says that if you think about a closed surface, so that might be the outside of a soccer ball or a football or some other closed surface, doesn't have to be a symmetric shape, could be any shape. It's got to be closed, not got to have holes in it. The flux through a closed surface is equal to the charge inside the closed surface divided by epsilon naught, that electric permittivity, that constant of nature that goes along with the electrical interaction. And so if you want the flux through a closed surface, all you have to do is add up the charge through inside the closed surface, or vice versa. If you knew the flux through the closed surface, it tells you how much charge is inside the closed surface. Here's an example of electrical flux and electrical field lines. So in this question, we're asked to look at this sketch over here on the right-hand side of an arrangement of two charges. So it's Q1 and Q2. Yeah, I don't know why I wrote Q3 here, but anyway. Q1 is the charge below, and we see field lines terminating on Q1, and Q2 is the field above. We see field lines emerging from Q2. And we're asked to figure out the ratio of Q1 to Q2. Now that ratio has a magnitude to it that depends on the sizes of the charges, but it also can have a sign to it, depending on whether the charges are like charges or unlike charges. So the key point here is that charges are a source or sink of flux. And the amount of flux, or the number of field lines coming from a charge, is in proportion to the amount of charge. So if you were to count up the field lines for these two charges, you'd see that there are 6 field lines terminated on charge Q1. There's 18 field lines emerging from charge Q2. So firstly, charge Q1 with 6 field lines ended on it is 3 times smaller in magnitude than charge Q2, which has 18 field lines coming out of it. And secondly, field lines are going into charge Q1, so it's negative. Field lines are coming out from charge Q2. It must be positive. And so they have opposite signs. And so that led me to the ratio here. This should be Q2. Of Q1 to Q2 is minus 1/3. Q1 is in size 3 times smaller amount of charge than Q2. Q1 is negative. Q2 is positive. So the ratio is minus 1/3. Okay. So I'm just looking at the chat now. So the ratio is negative because the charges are opposite. Yeah, that's exactly right. Yeah, if you've got one negative charge, one positive charge, then when you take the ratio of those two numbers, you're going to get a negative number. If they were both positive, or if they're both negative, when you take the ratio, you're going to get a positive number. Okay, now let's talk about the sort of classic application of our understanding of electricity and electrical forces and electrical potentials, which is electrical circuits and components in electrical circuits. So we started by talking about some simple circuits that just involve a battery and a resistor in this sketch here. And this slide is just to remind you how we kind of think about a battery and how we think about a resistor. So a battery, we think of, one way of thinking about it is as a source of a electrical potential difference that causes a electrical current to flow if there's a circuit connected across the terminals of the battery, across the electrical potential difference of the battery. So that's one way we can think about a battery. Another way we can think about a battery is that a battery is something that supplies electrical energy to a circuit. It supplies electrical power to a circuit. So that's the second way we would think about, visualize a battery. A resistor, a couple of ways that we think about resistors. We think about electrical resistance or resistance as something that impedes the flow of electrical current. So it's a little like in a mountain stream. Imagine that beautiful mountain stream. There's boulders and rocks in the stream. They're impeding the flow of the water down the mountain stream. In the resistor, it too is like a beautiful mountain stream. There's electrical current, electrons, say, flowing through the resistor, and there's boulders and rocks that are the ions of the resistor that are impeding the flow through the resistor. So that's one way of thinking about resistors. The other way of thinking about resistors is that resistors are devices, circuit devices that dissipate electrical energy. They don't destroy it, they turn it into thermal energies. Resistors get hot. They dissipate electrical power. They don't destroy the power, they turn it into thermal energy, into heat energy. So, you know, in a stove, right? In the oven of the stove is a filament that you use to warm the, I don't know, beef bourguignon or whatever you're making tonight. That filament is a resistor, and electrical energy, electrical power is dissipated in that filament or that resistor, and it's turned into heat, thermal energy, and that's how you're cooking your chicken Kiev or whatever you're doing this evening. Okay. One of the big discoveries about resistors that allows us to quantify how resistors work is Ohm's law. And Ohm's law, Ohm's law is simply a law, empirical law, based on the fact that if you apply a voltage across a resistor, a potential difference across a resistor, an electrical current flows through that resistor, and that electrical current is in proportion to the voltage. So if you double the voltage across a resistor, then you double the current through the resistor. If you triple the voltage across the resistor, then you're going to triple the current through the resistor. And the coefficient of proportionality between the current and the voltage is the resistance of the resistor. And that's what we call Ohm's law. So here's Ohm's law. The resistance of the resistor depends on a number of things about your resistor. It depends on the material that you've made your resistor from. And that dependence is encoded in a quantity called the resistivity rho. It depends on the length of your resistor. It depends on the cross-sectional area of the resistor. And those are the quantities L and A in this equation here. And so this sort of ancillary equation here for the resistance tells you the resistance of a particular resistor in terms of the resistivity of the material, the cross-section of the material, and the length of the material. It says things like, if you have a longer wire, right, that will have a greater resistance. If you have a greater cross-section wire, because in the denominator, you will have a smaller resistance. So all that's encoded in that equation here. It tells you that copper wires and aluminum wires and gold wires, they have different resistances because they're different materials with different resistivities. Okay. As I mentioned, that a resistance dissipates energy, dissipates power as the electrical current flows through the resistor. And those individual electrons collide with the ions of the resistor. That's the process of dissipating energy, dissipating power, turning energy into thermal energy, turning the electrical power into thermal power. So there were a couple of equations. I just want to really just mention these equations for the electrical energy dissipated in a resistor, the electrical power dissipated in a resistor. The electrical energy is this equation over here on the left-hand side. Electrical power dissipated in the resistor, this equation over here on the right-hand side. The energy dissipated is the potential across the resistor divided by the charge that flowed through the resistor. More often, we use the power, the rate at which energy is dissipated in a resistor. That's equal to several ways you can write it. The product of the current and the voltage across the resistor and through the resistor. Or you can rewrite it using Ohm's law, V equals IR. You can write it instead of in terms of current and voltage, you can write it in terms of current and resistance or voltage and resistance. So alternate versions here. Anyway, these two equations on the left and right, when you're looking at a resistor and you're thinking of it as a device, an instrument that dissipates energy and dissipates power, these quantify how much energy it's dissipating, how much power it's dissipating. This guy on the left for energy, this guy on the right for power. Okay. We talked in class about two circumstances where we arrange resistors in parallel and we arrange resistors in series. And I just wanted to remind you of that because those are basic building blocks of electrical circuits with resistors in series, resistors in parallel. Resistors in series is shown in this slide here. And resistors in series means that if you connect them to a battery, the current that, or an electron, say, that's flowing around the circuit has to pass through both resistors to get back to the battery. So that's what we mean by series. And a useful concept of our two resistors here in series with one another is a single equivalent resistance. That's R with EQ, equivalent as the subscript. And that's the resistor that for the same applied potential across the pair of resistors, or the equivalent resistor, draws the same current as the pair of resistors through the equivalent resistor. That's what an equivalent resistor means. And when you analyze circuits, it's often very helpful to replace resistors in series, resistors in parallel with their equivalent resistor to understand the electrical circuit. And that's why we use equivalent resistors. Now, there's a couple of key things I just wanted to remark for a pair of series resistors and their equivalent resistor. For the pair of resistors in series, the same current has to flow through both resistors. Each electron has to flow through both resistors. So the current through resistor 1, I1, current through resistor 2, I2, is the same as the current through the equivalent resistor, I. The two resistors, on the other hand, they share the electrical potential. Whatever electrical potential is applied across the circuit and is applied across the equivalent resistor, part of it is shared by resistor number 1. Part of it is shared by resistor number 2. So that's the second equation here. As a consequence of that key, right? This is key. Here's a couple of facts that emerge from that. The most important one really is that the equivalent resistance of the equivalent resistor is just the sum of the resistances of the individual resistors. So this allows you to replace this rule. This equation allows you to replace this pair of resistors in this circuit with this single resistor in this circuit. And that's in general how we analyze circuits. And so that's resistors in series. The other arrangement of two resistors is two resistors in parallel with one another. And so that's what I'm showing on this slide. This is a parallel resistor arrangement. And in a parallel resistor arrangement, over here on the left-hand side, an electron from the battery that flows around the circuit can either go through, say, resistor R2, the bottom one, or resistor R1, the top one. So the electrons can travel different paths around the circuit. That's what we mean by parallel. Again, there's a concept that the pair of resistors in parallel can be replaced by a single resistor, one that draws the same electrical current for the battery for the same resistance applied across its terminals. So that's what we mean by the equivalent resistor. So the kind of understanding of how parallel resistors work is the following. They share the electrical current. So those two resistors share the electrical current, but that's this equation here. Some fraction of the current flows through R1, that's I1. Some fraction of the current, remaining fraction, flows through R2, that's I2. What they don't share, what they each receive, is the full voltage of the battery. And so this battery's voltage is applied across both R1 and R2. And it's also applied across the equivalent resistor here. And based on this understanding, so this is the key to understanding this circuit. Again, it's all about how current and voltage is or isn't shared, just like it was in the series case. It was about how the current or the voltage is or isn't shared, leads to the rule for how to combine resistors in parallel to get the equivalent resistance. Here's the rule for the parallel resistors, is that the inverse reciprocal of the equivalent resistor is the sum of the reciprocals or the inverses of the individual resistors, in this case R1 and R2. Okay, so that's how we understand circuits involving resistors in series or parallel. The other electrical component that we introduced when discussing electrical circuits, in addition to the battery, that is the supplier of energy and power, the supplier of electrical current, the driver of electrical current, and the resistor, that is the dissipator of energy and power, was the capacitor. So a capacitor is a device, electrical device, that has two oppositely charged plates, two oppositely charged conducting plates, and it we think of it as a device for storing electrical charge in the circuit or storing electrical energy in the circuit, really for storing both. It simultaneously stores charge and energy. Over here on the left-hand side was our kind of definition of the capacitance of a capacitor. And over here on the right-hand side is an example of a parallel plate capacitor and its capacitance. So if we start over here with the definition of capacitance, to say capacitor is a device with two oppositely charged plates. When you apply charge to the plates, plus Q on one, minus Q on another, there's an electrical potential difference between the plates, delta V. The capacitance is the ratio of the charge you placed on the plates to the electrical potential difference that appeared between the plates. And that capacitance can be large or small, depending on whether that particular arrangement of plates can easily store charge or more difficult for it to store charge, or easily store energy, or less easily store electrical energy. So the capacitance reflects how easy or hard it is to store charge and energy. And that's why the quantity, the capacitance, is a useful quantity. So that's this equation here defines capacitance for us. Over here on the right-hand side, now this is a specific type of capacitor. If you have a capacitor that's made of two parallel flat plates, area of the two plates is A, the separation between the two plates is D. That's called a parallel plate capacitor, and its capacitance can be written in terms of the geometry of the parallel plate capacitor. It's basically the area of the plates divided by the separation of the plates, multiplied by this constant epsilon naught, comes along with electricity. So you can see here, if you make the area of the plates large, that's going to give lots of room to store electrons or electrical charge. You're going to make a big capacitor. If you make the area of the plate small, then you've got to cram all those electrons or all that charge on those small plates. That's going to make a small capacitor. So you see how area affects the capacitance. You also see how the separation between the plates affects the capacitance. If you have a small separation between the plates, then the field between the plates only exists over that small gap between the plates. That doesn't cost much energy. So it's easy to store charge. If you have a large separation between the plates, then that field has to extend over that large separation between the plates. That costs much more energy. So that makes it much harder to store the charge. So small separation leads to a small capacitance. Sorry, small separation leads to a large capacitance. The D's in the denominator, because you don't have to extend the field over a very large gap. A large distance D That makes a small capacitance because you've got to extend that field over a large gap. So that was capacitance. Likewise, I'm going to go through this slide and the next slide really quickly. Likewise, because it's very much like the case of parallel series resistors, this is parallel and series capacitors. Likewise, you can put two capacitors in parallel with one another. Here's a sketch of it on the left-hand side. And you can think of those as being equivalent to some single equivalent capacitance. The equivalent capacitance stores the same amount of charge for the same electrical potential difference. So that's what we mean by an equivalent capacitance. That's this arrangement here. And the rule for the equivalent capacitance, I've written it down here, is that the equivalent capacitance for two capacitors in parallel is simply the sum of their capacitances. So when you put capacitors in parallel, you build a bigger capacitor that's able to store more charge, less energy cost. And so that's capacitors in parallel. Let's do the same sort of slide overhead for parallel capacitors. For series capacitors, that's this guy here. So this arrangement is two series capacitors. Look, here's two series capacitors. Again, you can use the concept of an equivalent capacitance that for the same amount of voltage applied across the pair of capacitors stores the same amount of charge. And again, if you follow that logic, you get a rule and an equation for the equivalent capacitance of a pair of series capacitors. And the equivalent capacitance, the inverse or reciprocal, or the equivalent capacitance is the sum of the reciprocals or the inverses of the individual capacitors. So that's the rule for capacitors in series. Okay, then we moved on to magnetism. And for magnetism, we, like in electricity, we sort of introduced what I call the field equation for how electrical forces work. Here was the field equation. It related to the electrical force to the field that conveyed the force, and this was the field equation. In magnetism, there's a similar understanding of how magnetism works downstairs here, that the magnetic force between moving charges or equivalently electrical currents is carried by a magnetic field. That's the B here. And so this is the field equation for magnetic forces. Like this was the field equation upstairs here for electrical forces. There's a complication with magnetic forces compared to electrical forces. So electrical forces are forces between charges that are scalar quantities. They just have a, they don't have a direction to them. Magnetic forces are forces between electrical currents or moving charges, which are vector quantities. They have a direction of the motion of the charge or the direction of motion of the current. And so that makes these field equations a bit more complicated. You see in particular this sine theta here. And that sine theta is, that theta in the sine theta is the angle between the direction of the field and the direction of the motion of the charge or the direction of the electrical current. So unlike the electrical field equation, where the only direction on the right-hand side of the equation, the field equation, is the field, on the right-hand side of the magnetic field equation, there are two directions. There's the direction of the current or the moving charge and the direction of the field itself. So that's why you get this angle theta that's appearing on the right-hand side of the magnetic field equations. The other important point about the magnetic field versus the electrical field is the electrical field between a couple of charges acts along that line joining the charges. Let me start again on this. The electrical field electrical force on a charge acts along the direction of the field or opposite the direction of the field, depending on whether the charge is positive or negative. On the other hand, the magnetic force on a moving charge or electrical current acts in a direction that's perpendicular to the directions of the field and the directions of the current or the moving charge. So the direction of the force for magnetism and the direction of the force for electricity follows these different rules. Okay, here's just a quick example of that. And I'm never sure whether this works properly in Zoom or not. But in this case, right, we've got a moving positive charge particle. It's traveling towards the right from the left. It's moving through a region of field where the field, the crosses indicate, is heading into the screen. And we got to figure the direction of the force in this situation. So this is a case of right-hand rule. So right-hand rule, I will point the palm of my hand in the direction of the motion of the positive charge. I'll curl my fingers in the direction of the field that's into the screen. And my thumb is now pointing upwards on this page. And so that would be the direction of the force on this positive charge. It will be up. If this was a negative charge, then it would be down. The direction of the force is reversed because the sign of the charge is reversed. And so that's an example, kind of the field equation, the directional nature of the field equation. I'm going to skip that one. It's a numerical example of electric and magnetic forces because I want to get on to induction. But first, I wanted to just mention a couple of equations on magnetic fields. There's a couple of famous magnetic field configurations that we discussed in class. There's a few of them. And so I just wanted to recap those here. Here's one of them. This is the magnetic field of a long, straight, current-carrying wire. It's this equation over here. And this equation tells you the strength of the field around a long, straight, current-carrying wire. So that field is in proportion to the current. So that's the I here. It's in inverse proportion to the distance from the current carrying wire. And then it's multiplied by this constant, mu naught over 2 pi, associated with the magnetic force. So this is the strength of the field. And then the right-hand rule, another right-hand rule, gives us the direction of the field. The field lines are concentric circles around the wire. You point your thumb in the direction of the current, and then your fingers curl of your right hand in the direction of the magnetic field. And so that's how we get the direction of this field. So that's one important field. Here's another important configuration of magnetic field. This is one that's created by what we call a long solenoid. It's many windings, circular windings of current carrying wire. And that's what you're seeing here on the left and seeing here on the right. The windings coming out of the page here on the left and back into the page on the right to form this coil or this solenoid. And that creates, interestingly, inside the solenoid, a uniform magnetic field. So this is a very important magnetic field. And there's an equation here for the magnitude of this magnetic field inside the solenoid. And it's quite interesting because it just depends on the current that's flowing in the solenoid. So it's in proportion to the current in the solenoid. And then this lowercase n here is the number of turns of the solenoid per unit length of the solenoid. So the number of turns per meter of the solenoid. It's not simply the number of turns. is how closely or densely those turns are packed. And so that's this quantity here. Okay, so that's the magnitude of the magnetic field of the solenoid. If you want the direction of the field, there's another right-hand rule for that. You curl your fingers in the direction of flow of the electrical current in the winding of the solenoid, and your thumb points in the direction of the magnetic field. So it's a similar right-hand rule as the last right-hand rule, but the role of current and field for your thumb and your fingers has reversed in this right-hand rule, and that's described here. Okay. We then moved on to induction, and power's going to run out of my laptop in one minute here, so I've got to unhook my pen for the moment to let it recharge. I think I can use the mouse to draw, but that's going to be extremely painful. But anyway, the next thing we moved on to was this unification of electricity and magnetism. I'm going to go through this slide and the next slide very quickly. We met a new effect. So this is a radically new effect from the electrical interactions, the magnetic interactions we've just been talking about. It's electrical interaction. It was discovered by Faraday, and Faraday's law is associated with this effect. If you have a loop of wire, a coil of wire, and for whatever reason, you change the magnetic flux through that loop or that coil of wire, you change the magnetic field in that coil or that loop of wire. At that moment of change, instant of change, you're going to get an induced current and induced EMF in that wire. Now, you might have changed it because you stuck a magnet in it, or you pulled a magnet out, or you might have changed it because you switched some solenoid on, or you switched some solenoid off. However you change the magnetic flux through that loop of wire, you get an induced current, an induced EMF that is in proportion to the rate of change of that magnetic flux. And that's Faraday's law. And that's this guy upstairs here. Let's see if I can do this with the mouse. This is extremely painful for me. So that's Faraday's law of magnetic induction. And it's just saying that when you change fluxes through a circuit, you're going to create induced EMFs, induced currents in the circuit. So one way that you can change the flux through a circuit is by motion, moving the circuit. And that way of changing the flux through the circuit is called motional induction. And here's an example of motional induction. If you take this loop of wire, right, and you rotate it in this magnetic field between these north and south poles of magnets, then that's changing the magnetic flux that's passing through this circuit. And so as you rotate this loop of wire, the flux is changing through this loop of wire. That's inducing an EMF in this loop of wire. And that's generating an electrical potential. It's generating an electrical current. It's generating electrical power. And it's how we make electrical power and energy in our power stations. So this is very useful to us. And here's the equation that goes with that induced EMF that's created by that changing magnetic flux. So the induced EMF is in proportion to how many turns of wire we have in our circuit here. So each additional turn will collect more flux, and so will induce more EMF. It's in proportion to the magnetic field. The stronger the field, the bigger the changing flux, the weaker the field, smaller the changing flux. It's in proportion to the area of the loop that you're rotating in the field, because the bigger the area, the more field lines you capture. The smaller the area, less field lines you capture. And then it's also in proportion to this piece here. So omega is how fast or slow you're rotating the coil. Obviously, if you weren't rotating it, there would be no changing flux, no induced EMF. If you rotate it really fast, there'd be a big induced EMF, a big changing flux. And so that's embodied in this piece here. Anyway, that's motional induction. Oops, didn't mean to do that. There's also a second type of induction. I got to get back in slideshow here, sorry. And that was this demonstration. And transformer induction, this is the other type of induction, is when you change a magnetic field by, say, switching on a coil of wire or turning off a coil of wire, you induce an induced EMF and induced current in another circuit. And so I'm going to switch on and off the large coil that you see in this picture. And that induces an EMF and a current in the long solenoid that you see in that. And so that's what we call transformer EMF. I don't think we can see your video. Oh, that's interesting. That is interesting. I hope you still see my slide. And the sound is bad. My sound? Well, the loud sounds are the sparks. I don't know if there's other sounds that are going on. Okay, so still see the induction slide. Do you see one that says analogy between inductors and capacitors? No. Let me reshare then, because I don't know what's going wrong here. Do you now see analogy between inductors and capacitors? No. Okay, let me somehow get out of all of this. So do you now, let's go back to basics. Do you see me? Yes. Okay, that's a minor success. Now, let's see if I can reshare. Do you see a slide with yes, yes. Okay. I don't know what happened there. That's the last time I'm going to try and show a video over Zoom. Associated with transformer EMF is the concept of inductors. So inductors are devices in which if you change the current through them, that changes the flux through them, which induces a EMF in the inductor. And these also are circuit components. And so we introduced the concept of inductance here on this slide. It's this lower portion here. And we introduced it kind of an analogy to capacitance in circuits. It's this half here. So I think of an inductor as something that if you pass a current through an inductor, you create a flux through the windings of the inductor, and the inductance of the inductor is related to that ratio, that flux and that current. Just like if you charge a capacitor, place charge on the place of the capacitor, create a potential between the place and the capacitor, and the capacitance of the capacitor is defined in terms of those two quantities. So there's a very famous capacitor. We've already talked about it. It's the parallel plate capacitor. That's over here on the right. And then there's also a corresponding inductor. It's a long solenoid or solenoid. That's this inductor over here on the bottom right-hand side. In both cases here, there's an equation for the capacitance of the parallel plate capacitor. There's an equation for the inductance of the long solenoid, where the two equations tell you how the geometry determines the capacitance of the capacitor, or the geometry of the inductor determines the inductance of the inductor. So that's a quick summary of that. We moved on from induction to talk about electromagnetic waves. So on this slide, I tried to summarize some properties of electromagnetic waves. Electromagnetic waves were predicted based on this unification of electricity, magnetism, through this process of induction. Putting those things together gave us the full electromagnetic theory, which gave us the prediction of an electromagnetic wave, which was identified with light being an electromagnetic wave. So this is a massive moment in science. The properties of light waves were there, and other electromagnetic waves was predicted, therefore, by electromagnetic theory. So light, let me just walk through some of these properties here. Light is a bundle of electric and magnetic fields that travels at a speed that's the speed of light. The electric field oscillations, the magnetic field oscillations, and the motion of the light ray are all perpendicular to one another. The strengths of the electrical field, the magnetic field, and the speed of light ray are related to one another. The ratio of the two fields equals the speed of light. And the speed of light you can calculate by this little equation here. The theory of electromagnetism predicts this little equation here, that the speed of light is the inverse of the square root of the products of the two constants associated with electricity and magnetism: the permittivity of free space for electricity, the permeability of free space for magnetism. Okay, here's a question. On the induction and Faraday's law slide, what determines the direction of the current as you pull the magnet away or push the magnet through the circuit? Yeah, so that's a good question. I don't have a slide on Lenz's law in my summary slides here, but you probably want to look at that in the lecture slides. So the direction of the induced current, induced EMF, is given by what's called Lenz's law. Lenz's law says that the direction of the current and the direction of the EMF, we normally think of the direction of the induced current, is one that will make a magnetic field. It itself will make a magnetic field. We'll call that the induced magnetic field, that will oppose whatever change is going on. So if you remove a magnet from a coil of wire, the induced current is going to try and make an induced field that replaces that field that you've taken away. If you put a magnet into a loop of wire, the induced current, the induced EMF, will create a magnetic field that tries to counteract that field that you've just cancel out that field you just put in the magnet. So the induced current always makes an induced magnetic field that's going to oppose the change, try and counteract the change. So I hope that helps. We started talking about some of the properties of light. Look, I've come to the end of the class time, so obviously it's up to you whether you want to continue to punish yourself with these slides or not. But I will continue to, if you remain, punish you with them until I get through the end of this. Okay, so that's it. If you want to leave, for sure, don't feel forced to stay. Which I'm presuming you don't feel forced to stay anyway. Anyway, so we talked about some properties of light, some characteristics of light. And these properties of light flow from our understanding of light as electromagnetic wave, although we don't always explain the details of how they flow. One property is reflection. So there's a law of reflection. Light reflects off a mirror or other shiny surfaces with a law of reflection, where the refraction states the reflected angle equals the incident angle, where these two angles measure the directions of the incident ray and the outgoing ray, and they're measured with respect to a line that is perpendicular or normal 90 degrees to the surface off which you're reflected. So this is the law of reflection. And then there's a corresponding, another process that's called refraction. That's when light travels from one material to another material. So maybe the light is going from air to glass, or air to water, or water to glass, or any other combination of different optical materials that you can actually dream up. Light in general is bent when it moves from one optical material to another optical material. The directions in the two materials are related to one another. The directions are characterized again by angles with respect to the normal, to the surface, the bounding surface between the two materials. So there's an angle in my sketch here, theta I, an angle theta R. These are the incident angle and the refracted angle. And the relationship between them is determined by two numbers that characterize the optical properties of the materials. They're the refractive index of the incident material. I call it Ni here. We sometimes call it N1. That's the refractive index of the refracting material. That I've called it NR here. It's often called it. We often use N2. And down here is Snell's law of refraction that relates the directions in the two materials to the refractive indices of the two materials. So that's the law of refraction. I'm going to plug back in my pen so I can start my pen work again. So that's, as I say, that's the law of refraction. There's one little extra piece of information that you need with the law of refraction. Now, when you reflect, the reflected light has the same wavelength, the same frequency, the same speed as the original light, the incident light. When you refract, the speed is different. It could be larger or smaller, depending on the refractive indices of the two materials. And also the wavelength can be shorter or longer, depending on the relative size of the refractive indices of the two materials. But the frequency of the refracted ray and the incident ray, those are the same. And that's all embodied in this set of equations here about the speed, the wavelength of the frequency of light rays in optical materials with refractive indices N. Okay, so we took our laws of reflection and refraction and applied them to mirrors informing images and to lenses informing images. And so the next few slides are just quick summaries of mirrors informing images and lenses informing images. So when we form images with mirrors, a curved mirror is characterized by what we call a focal length. And the focal length of the mirror is related to the radius of curvature of the mirror. But this focal length F is kind of like the personality of the mirror. So firstly, it has a sign. So if the mirror converges the light rays towards the optical axis, then that converging mirror, that has a positive focal length. If it bends the light rays away from the optical axis, that's a diverging mirror, and that has a negative focal length. If it strongly converges, that would correspond to actually a small focal length. If it only gently converges, that's a large focal length. And the same for diverging. If it strongly diverges, that's a small negative focal length. If it diverges just gently, then that's a large negative focal length. So that's the personality of the mirror, described by the focal length. And then once you have that focal length, you can calculate image formation by mirrors and understand image formation by mirrors with using that focal length and this pair of equations here. So this pair of equations we use for mirrors and the images that are formed by mirrors. There's the mirror equation and there's the magnification equation. The mirror equation relates the location of the image, that's the P here, location of the object, that's the Q here, to the focal length of the mirror. And then the magnification equation, the second equation here, relates the magnification, how much bigger or smaller the image is compared to the object, to the positions of the image in the object. That's again the P and the Q here. And so these are the equations that describe images formed by mirrors. I'm not going to go through these details of this here. We also learned in class how to sketch the formation of images by mirrors. And we would do ray tracing to find the images formed by mirrors. So will the final be 50% new material and 50% old material? No. The final is 1/3 material on the first test, 1/3 material that was on the second test, and 1/3 the new material. 1/3, 1/3, 1/3 to answer that question. So we also talked about images that are formed by lenses. And here's the corresponding, oops, jumped ahead, equation and picture of this focal length of a lens, corresponding like to the focal length of a mirror. So the focal length of a lens, which is kind of its personality, is described by this equation here. It's more complicated. It's more complicated because it involves the refractive index of the material you made the lens out of, because now refraction, not reflection for lenses. And also there's radii of the front and the back surfaces of the lenses. So there's 2 radii rather than just the 1 radius of the mirror. So it is a more complicated equation. But again, it tells you the focal length of a particular lens. And again, if the lens is converging, if it bends light towards a optical axis, that's a positive focal length. If it strongly bends the light towards the optical axis, then that's a small positive focal length. If the lens is such it diverges light away from the optical axis, that's a negative focal length. If it strongly diverges the light away from the optical axis, that's a small negative focal length. So the same sort of rules for the mirror about what focal lengths mean. And actually, there's the same set of equations for the images formed by lenses as there were for images formed by mirrors. So that's an important point. If you look, this is a sketch of images formed by mirrors, by lenses. Again, there's the same equation. Now we're calling it the lens equation for the relationship between the location of the object, location of the image, and the focal length. And there's the same magnification equation for the lens that relates the magnification, how much bigger or smaller, minified or magnified, the images compared to the object in terms of the object position P and the image position Q. Just a couple of remarks about converging mirrors and lenses and diverging mirrors and lenses. So converging mirrors and lenses, they can make magnified and minified, bigger and smaller images. They can make what we call real and virtual images. Real images you can actually focus on the screen. Virtual images just appear to come from a location. You can't focus them on the screen. And they can make both upright and inverted images. That's not true of the diverging lenses and the diverging mirrors. For example, diverging lenses and mirrors only ever make minified, smaller smaller objects, smaller images of the objects. And so they're much less flexible than the converging lenses and the converging mirrors. What makes, okay, here's a question. What makes the focal length negative for diverging? Well, that's more a convention. So in our equations, when you use these equations, when you use the lens or mirror equation, when you use the magnification equation, the convention for using them is that diverging focal, something that diverges, a mirror or a lens, has a negative focal length. Something that converges has a positive focal length. And as you know, and you'll get a table of conventions with your exam. There's also conventions about the meaning of positive object, negative object positions, positive or negative image positions, and so on and so forth. You could choose, if you wanted, a different convention. And as long as you stick to it, it would be okay. But we normally always stick to the same convention, that diverging is negative, converging is positive. It's a bit like, right, this would be an analogy to that, you know, when we discussed objects falling under gravity, you could choose upwards to be the positive direction, or you could choose downwards to be the positive direction. That's a convention. As long as you're consistent with that choice when you work with the positions and the velocities and accelerations, you get the right answer. Likewise, our convention about focal lengths and diverging and converging being negative and positive focal lengths is a convention. As long as we're consistent with all the conventions that go along with that, about object, positive and negative signs, image, positive and negative signs, we'll get the right answer. So it is a convention. We could use another convention, but we never do that with lenses and mirrors. I don't know whether that helped or that didn't help, but it is a convention. Yeah, real images versus virtual images. So a real image, this sketch here shows the formation of a real image. So these rays here from this object on the left forming this object on the right, image on the right, they really go through, they really do pass through this point. And that's what we mean by a real image. When you have a virtual image, I don't know if the previous one had that. No, unfortunately, this one's a real one too. A virtual image, when your eye traces back the rays, they appear to come from a location, but it might be behind the mirror. So they can't really come from there. Or they appear to come from a location behind the lens where they don't really come from. So that's the two classes of images. One where the light actually came from the place where you're seeing the image. One where the light, it just appears to come from the place where you see the image. So concave, converging can be real or virtual, inverted or upright, shrunken or magnified. Yes, that's a completely, depending on where you put the object for a converging lens or a converging mirror, you can get real or virtual, you can get inverted, upright, and you can get minified or magnified. What is diverging? Okay, so when you have a diverging, you can, now you're testing my memory whether I'm going to get this right. When you have diverging mirror or lens, you can only minify, so you can only reduce the size. I think that you can only make virtual images. So for example, a diverging mirror will always make an image that is behind the mirror. And then the what is the final way? So we said that it's going to be virtual. We said that it's going to be minified. And I think it's always upright. That's the one I can't quite remember. I believe it's always upright, but we better check that. If you look in my slides for the diverging mirror, the diverging lens, you'll see I know I wrote this down in the slides, so I think I would double check that. My notes say minified, virtual, upright. That sounds right to me. Is that what I had just said? Maybe I said minified, virtual, inverted, but I think minified, virtual, upright. That sounds right. Okay. I'm plugging back in my laptop power again. I need to get a better way of doing this. Let's push on before we all pass out. We talked about this question, is the review going to be recorded and is it going to be posted? I believe I am recording it. I hope I'm recording it because I said I would record it. Yeah, it says, do I want to pause recording? Yeah, so I am recording it and I will post it when I get the email that it's available. So sometime later this afternoon. We talked about two effects, interference and diffraction, two phenomena, interference and diffraction, that are characteristic of waves. So sound waves, water waves, they interfere, they diffract, that are not characteristics of particles. Particles don't interfere and particles don't diffract. And so the diffraction, the interference, were important historically in identifying that electromagnetic radiation, light, had wave-like properties. And here in this slide, I'm just showing you that interference and diffraction are characteristics of waves, but not characteristics of particles, by showing you particles illuminating these two pair of slits here on the left-hand side. Waves, these are wave fronts illuminating these two slits on the right-hand side. When the particles stream through, firstly, then their direction isn't changed by the obstacles. The ones that get through just go straight through. So that's the absence of diffraction. When the waves go through the obstacles, through the slits, their paths are changed. They're bent. They emerge radially outwards from the obstacles. So that is diffraction. And then the second thing that happens is that when the waves go through the obstacles, those waves coming through the two slits, they interfere with one another. So crest meets crest and you get constructive interference. Crest meets trough and you get destructive interference. There's no such thing for the particles. There's no interference of particles. Particles can collide with one another, strike one another, but they don't interfere constructively, destructively with one another. So that's an important characteristic of waves, diffraction, interference. That's not a characteristic of particles. There's no diffraction or interference. So that's a way, that's a manner in which we can distinguish waves from particles. We talked about, as examples of interference and diffraction, the patterns of fringes that you get from a shining light on a single slit, where you get diffraction by the slit, shining light on a double slit, where you get diffraction followed by interference with the double slit, and then shining light on many slits, or what we call a diffraction grading, where you get, again, a characteristic diffraction pattern. And I tried to summarize them here in these three equations. These were the formulas for the fringe patterns from a single slit, that's where you get diffraction. Double slit, that's where you get diffraction and interference. And a diffraction grating, again, that's where you see, okay, so it looks like I'm still stuck on the lens slide. Let me see if I can, let me exit again. Do you see the new slide now? Okay. So this slide, I'm trying to, as I say, summarize the equations associated with diffraction and interference through a single slit, a double slit, and a multi-slit or a diffraction grating, which are the three arrangements that we discussed in class. And there are three corresponding equations here. And there's a lot of similarities between these three equations, but there's also subtle differences between these three equations. So you do have to be a little bit careful in using these three equations. So let me just get the pen going again here. In the single slit case, so this one here, this A is the slit width. So that's important. For the single slit diffraction, it's the A is the slit width. In the other two cases, this D here, that's the spacing between the splits. That's slit separation. So that's one difference. A second difference is that in the single slit, this angle here is the location of the dark fringes for the single slit. In the double slit and multi-slit, this angle here is the location of the bright fringes. So that's an important difference. Again, you get bright and dark fringes when there's whole numbers or half integral numbers of wavelength differences between the paths that are taken by the light going through the different slits. And so that's how these patterns emerge. Okay, now the final couple of topics are those two topics in modern physics that we discussed. One of them was relativity, which was sort of a revolution about 100 years ago in our understanding of space and time. And then the other one was another revolution. It was a revolution, what we call wave-particle duality, which was a revolution in our understanding of sort of things on the scale of atoms or molecules or subatomic particles. So two big revolutions. So let's start with the relativity one. And that's this slide here. So just as a starting point for us in understanding relativity, I just want to mention this concept that would come up in Physics 211, which is reference frames. So reference frames are basically coordinate systems from which we measure positions of objects, times of events, and calculate velocities or accelerations, all those sorts of things. It's important that when you calculate, say, the velocity of an object, like a ball, you're calculating it from the perspective of a reference frame. And it's important in relativity that different reference frames are equally valid. And that's what I'm trying to show here in this picture. I'm imagining two reference frames. One, the pedestrian on the platform has his or her reference frame. One, the passenger in the train has his or her reference frame. Here are those two reference frames in red and black. I'm just showing one space dimension and the single time dimension. They're moving with respect to one another, but one's not more privileged than the other one. One's not more valid than the other one. They're both perfectly valid. And it's important that when we measure velocities, they're always measured with respect to a reference frame. They're always measured with respect to something. So, you know, in our everyday life, I lie on the sofa, I think I'm not moving. And I get in my car and I think I am moving. That's just because I'm moving with respect to, or not moving with respect to, the earth. So I'm really saying I'm not moving when I'm on the sofa, or I am moving when I'm in the car with respect to the earth, right? So that's an example of how ingrained reference frames are. In reality, there's no privileged reference frame that is, you know, the one to quote velocities in, and that other reference frames are somehow less privileged for quoting velocities in. Okay, so the two important effects that we talked about for space-time in relativity were time dilation and length contraction. So to imagine time dilation, imagine that passenger on the train and that pedestrian on the station, and imagine them looking at the station clock. So the pedestrian on the station sees the clock as stationary. The passenger in the train sees the clock as moving. In relativity, they don't both see the clock tick at the same rate. The pedestrian looking at the stationary clock sees the proper time, what we call the proper time between ticks. The passenger in this train sees what we call the dilated time, a kind of slower time between ticks. And the relationship between the proper time and the dilated time is given by this little equation downstairs here that I just jumped over. This equation downstairs here is the equation describing time dilation. So over here on the left, this is the time between ticks observed by the passenger looking at the station clock. And over here on the right in green, this is the time between ticks observed by the pedestrian seeing the stationary clock. And the time between ticks is slightly longer for the passenger and slightly shorter for the pedestrian. And it depends on the motion of the passenger with respect to the pedestrian. That's the V here. That motion compared to the speed of light. That's the C here. So this effect vanishes if you're at everyday speeds, because V squared over C squared is essentially zero. But this effect becomes important if you're going at speeds near the speed of light. Then this time does get dilated for the clock ticks. Now, it's important to say that if they were, instead of looking at the station clock, they were looking at the train clock inside the train, then the train passenger would see that the proper time at the train clock, and it would be the pedestrian that see with the dilated time of the train clock. So again, there's no special reference frame. The station isn't a special reference frame, or the platform isn't a special reference frame. The train isn't a special or a privileged reference frame. Any reference frame is valid, but if you're looking at a stationary clock, you measure the proper time. If you're looking at a moving clock, you measure the dilated time. This just shows you the factor by which times are dilated. It's called the Lorentz factor. So I say, if you're at slow speeds compared with the speed of light, everyday speeds are way over here on the left, that factor is 1. But if you're at speeds near the speed of light, that's way over here on the right, that factor is much bigger than 1. So time really slows down. The ticks of that clock would really slow down if that train was moving at near the speed of light. The other effect in space and time that we talked about was length contraction. So it's a similar effect, but not for the time interval between, say, ticks of a clock, but rather the distance interval between 2 points. So if we imagine a station meter stick at rest on the platform, the pedestrian sees the proper, what we call the proper length of the meter stick, and the passenger in this train that's moving, sees a moving meter stick, will see a contracted length of the meter stick. So that's length contraction. And then again, there's an equation for that length contraction effect. Here it is. It looks rather similar, except we're multiplying by this square root factor instead of dividing by it. So this is why lengths contract, but times dilate. But again, it tells you that it depends on the motion of the meter stick. So that's the V here, compared to the speed of light. That's the C here. So at everyday speeds, this quantity here is just zero, essentially. And they agree on the length. But if we were at relativistic speeds, where this factor here is not negligible, then there is significant length contraction. And that's shown on the next slide. Here is the factor by which length is contracted. Again, this is this now is this 1 over the length, the Lorentz factor. So it's this factor here in the square root of 1 minus v over c squared. And it says that, you know, if you're at everyday speeds, that's way over here on the left, this factor's 1, there's no length contraction that's observable. But if you're at speeds approaching the speed of light, this length contraction can be very large. So look at the scale of the length contraction as you get towards the speed of light. 99% of the speed of light. It's a huge effect of length contraction. Because we changed our notion of space and time, the end result was that we had to change our formulas for momentum and energy in mechanics, classical mechanics, from the classical mechanical expressions for momentum and energy to new relativistic expressions for momentum and energy. Now, I should say that we never, figured out these new equations for momentum and energy. I just quoted these new equations for momentum and energy because the derivation of them is beyond the scope of physics 211 and 13. But anyway, we need new equations. For momentum, the new equation is this one I've quoted here. Instead of momentum being just the product of mass and velocity, relativistically is the product of the Lorentz factor and the mass and the velocity. So there's this one extra piece in it here. At low speeds, this piece is 1. The Lorentz factor is 1. And so at low speeds, the relativistic equation becomes the classical equation. But at high speeds, gamma gets bigger than 1, much bigger than 1. As you approach the speed of light, the gamma factor approaches infinity. And so it changes the relativistic momentum. It's what, so in relativity, you have unlike classical mechanics, in relativistic mechanics, you have a speed limit. Nothing can go faster than the speed of light. And this equation helps you with that speed limit. Because as you exert more and more force on a particle to try and make it go faster, what happens here is you don't make it go faster anymore. You just give it more momentum. The force transfers the momentum, but it barely gets any faster. So this equation prevents the speed of an object experience of force going larger than the speed of light, but it allows the momentum of that object to get larger and larger, approach infinity as you exert a force on it. Okay, another famous equation that came out of relativity, and one that you would know about from kindergarten, is E equals mc squared. It's very famous, everybody knows this equation. This equation says that matter is actually a form of energy. Matter is, not just some amount of substance or something that says how easy or hard it is to change the motion of that something, but matter is actually a form of energy. Like kinetic energy is moving energy, or like electrical potential energy is a form of energy, magnetic energy is a form of energy, gravitational energy is a form of energy, matter, mass is a form of energy. And this is the equation that tells you how much energy is in how many kilograms of matter, equals mc squared. So it's very important because it told you that in all the material around you, all the matter around you, there's huge stores of energy because c squared is such a big number. It tells you that actually when you have a chemical reaction, the mass of the products, if that chemical reaction releases energy, releases heat, it's the fact that the products of the chemical reaction are slightly less massive. The reactants in the reaction, the parents of the reaction, they were slightly more massive, and you turn some mass energy into thermal energy, heat energy in that reaction. And that's famously true in sort of nuclear reactions, nuclear power, nuclear bombs. In a nuclear bomb, what's happening is that you're turning some of the mass energy of the atoms and molecules in the bomb into thermal heat energy. So the products of the nuclear reaction have less mass than the parents in the nuclear reaction. And we talked about an equation in relativity that told us quantitatively about energy in relativity and how we needed to modify the equations for energy and relativity. Here it was, right? And if I read across this equation here, it says that now we understand that, a moving object, but it really has two moving particles, say it has two forms of energy, a rest energy associated with its mass and a kinetic energy associated with its motion. The total energy is gamma mc squared, the Lorentz factor times mc squared. The mc squared piece of it, that's the rest energy. The remaining piece of it, that's the thermal energy. And so that was our relativistic energy equations. Again, we had to modify them from our classical energy equations because of this change in space-time. Finally, we talked about, this is the last couple of slides here. I can see that we're all dying off, basically. We talked about wave-particle duality. That light is not just a wave, it exhibits particle-like properties, and electrons are not just particles of matter, they exhibit wave-like properties. We talked about the evidence that light has particle-like properties. The first evidence was black body radiation. To explain this black body spectrum associated with black body radiation as radiation that is emitted by everything, that depends on the temperature of objects, strongly on the temperature of the objects. To explain that spectrum of black body radiation, we found that the energy that's emitted in the black body radiation is emitted in little packets, where the packets are given by that equation from Max Planck, which was that the energy packet is Planck's constant times the frequency of the radiation, so HF. So that was one step. And then the second step was the photoelectric effect. So the photoelectric effect, to understand the photoelectric effect, we had to understand that the electrons that are knocked out of a metal by light are actually knocked out by particles of light, striking the individual electrons in the metal. In that way, we can understand the photoelectric effect. So at that point, we had to recognize that light is both emitted and absorbed in packets, and also propagates in packets, because we're seeing these packets of light strike electrons in the photoelectric effect. And so that was kind of this granularity, what we call the photons of light. We then also saw for a matter that matter has wave-like, of a kind of waviness to it. This was first just a hypothesis by a scientist called de Broglie, who came up with the hypothesis that a particle with momentum p has a wavelength that's given by this equation here. The wavelength is Planck's constant divided by p. So he hypothesized that. But it was soon observed that electrons, for example, have an associated wavelength, because the interference of electrons, the diffraction of electrons from crystals, from electrons striking crystals, was observed. So that was a big step forward to see that electrons, which were thought to be particles, do exhibit wave-like properties. I'll skip that one for the moment. Putting together the wave-like properties of matter, so electrons, and the particle-like properties of light, photons, gave us finally an accurate model picture of the atom, and it's called the Bohr atom. So in the Bohr atom, the electrons are orbiting the nucleus, but their corresponding waves have to fit precisely in that orbit. And so that restricts the radii and the speeds of the orbits to certain values, certain allowed values. And that restricts the binding energies and the angular momenta of the electrons in the atom to certain binding energies and certain angular momenta. And I've quoted those equations here. So here is here's the allowed energies of the electron, binding energy of the electron in a hydrogen atom. Here's the allowed angular momenta of the electrons in the hydrogen atom. And it's all a consequence of electrons having both particle and wave-like properties. So as a result of that, there's only certain orbits that are allowed for electrons in, say, a hydrogen atom. Let me show you those orbits on the next slide. Here they are in the form of what we call an energy level diagram. So the horizontal lines here represent the allowed orbits. The orbits are labeled with a quantum number, n. The ground state, the most bound state, the lowest lying state is n equals 1. The first excited state, that's the next lowest lying state, that's labeled with n equals 2, and so on and so forth. So 3, 4, 5. Over here on the right are those allowed binding energies. They're very specific. Minus 13.6 is the binding energy of the ground state of hydrogen. Minus 3.4 electron volts, the first excited state is hydrogen, and so on and so forth. And transitions between these different orbits can occur. So you can excite an electron from a lower lying level to a higher lying level by absorbing light. You can de-excite an electron from a higher lying orbit to a lower lying orbit by emitting light. And so this wave particle model of the hydrogen atom says that the hydrogen atom emits just certain characteristic colors of light, and it absorbs just certain characteristic colors of light. And we can calculate the frequencies and the wavelengths of those colors with these equations down now here. So over on the left-hand side are the frequencies and the wavelengths of the light that are emitted and absorbed by hydrogen. Over on the right-hand side are the quantum numbers of the states corresponding to the transition. So a de-excitation from a higher state to a lower state, its principal quantum numbers, or an excitation from a lower lying state to a higher lying state, its quantum numbers. So they're described here. Okay, that's it. That's what I had. We did a grand tour of electricity, magnetism, induction, the unification of electricity and magnetism, and prediction of electromagnetic waves. We talked about the properties of light, reflection, refraction, diffraction, interference. We've led to the modern physics of the revolutions in space and time, in wave particle duality. So we talked about relativity and time dilation and length contraction and relativistic energy and relativistic momentum. And then finally, we've ended here with the wave-like properties of electrons, the particle-like properties of photons, and the sort of combination of that being the the model, the wave particle model of the hydrogen atom. Okay. Also, thanks for those of you that stuck with me through that. I appreciate it. Any questions that I can answer now on all that material? Are we close to getting the lecture evaluation bonus? Oh, that's a good one. Yes, it's really close. I started to look, and they're all scattered around 80%. So I get reports from different sections. So there are a few below and a few above. So I think I didn't calculate whether it was exactly there, but I know it's very close to being there. If you haven't done it yet, please do it. But I'm pretty sure we're going to cross that boundary either today or tomorrow. Well, thanks, everybody. I need a margarita or something after that, but and probably everybody else does. Thank you.